or not? Oh, why? Great. So I'll start with this introduction to the modern physics, so give you a hint of where we have arrived, which are still part of the mysteries. Of course, you will hear much more in the coming days and today from my colleagues about some of these arguments. We try to do a program which embraces part of these mysteries, starting from the dark matter or dark side of the universe. There are two talks related to this. One is given today and one in the other days. There are some talks related with some applications of the quantum mechanics. So quantum mechanics is a theory which is very, very successful, but for some sense it's very still mysterious because it has not yet reached a consensus among researchers of what's the deep meaning of the things which are described within the quantum mechanics. And there are talks about the gravitational waves, and you have already seen the program, so I don't bother you anymore with this. One thing which I have to tell you is that this is a special year. Probably some of you know that it's the so-called International Year of Light, and this means that this year has been declared by the United Nations Educational, Scientific and Cultural Organization, UNESCO, the International Year of Light, exactly, and there are many, many activities ongoing in all the countries in Europe and in other countries out of Europe as well, and this is a special occasion to celebrate, and that's one of the reasons for which part of our presentations are directed towards this. And you have seen before Fabio Bossi, who gave you a kind of, a welcome on behalf of the research division of Frascati. He will give you as well a talk, a scientific presentation about the so-called dark photon, so the dark light. Okay, so this is just to start that since you are here, I assume you share what Michio Kaku, who is a great physicist, but it's in the same time, he writes very nice book of science for public. I think you share the fact that you want to know, we want to know. So he says that it must be a strange world not being a scientist, going through life not knowing, or maybe not even caring about where the air come from, where the stars at night come from, or how far they are from us. Actually, if you think, you look at the star, now we can indeed reach the measurement of the distance. We can know, we have the means to know how far the stars are. And this by itself, it's such an enormous achievement. So he says, of course, I want to know. And since you're here, I bet you want to know. Maybe you want to know many things, not only in physics. I presume and I hope, actually, that not all of you will become physicists. So it's just, by the way, who wants to study physics? Oh, gosh. Good. Who doesn't? Come on, don't be shy. Okay, that's good, that's very good. So those who want to study physics, as well as those who do not want to study physics, it's equally important to be curious about so many things in life, and you're at the right age to not only to be curious, but to transform your curiosity, not only in something interesting and important for yourself, like a kind of a job, even if for me it's hard to say my job is being a physicist. There is no job like being a physicist. It's only a passion. You have sometimes the fortune to be paid to put forward, but there are many other things, biology, medicine, genetics. So it's many ways to be curious. So now being curious, let's see what the physicists, what the scientists succeeded to do. So we have I will talk mostly about the modern physics, and the modern physics has some pillars which are very strong, but it's not said that they will stay there forever. Maybe we will find some better theories, which I'll show you some of the points which are, let's say, making us believing that the theory we have today, in spite of the success, should not be the final one. So the pillars are going deep, are deeply rooted in the relativity, which is a very weird theory if you think about just when you wake up in the morning. And this happens to me as well. It's not only to the first time you hear it that you become, wow, it can't be that space-time behave like that. And, but we have reasons not only to believe, we have checked and touched by hand, and I'll tell you, I'll convey to you why this is so. So we will go from the relativity, and the relativity related again with the light, because reminding the year of light, all these achievements were brought to us by understanding the light, so starting to wonder and to question, and Einstein was certainly one, not only one, but one of those who succeeded to arrive farther, very far, and farther than others in thinking about the light. And now, of course, we can even think and imagine and make some fantasies about interstellar travels, so go very, very far, which, well, farther than certainly we can go today, because today we didn't reach too far. Our objects like Pioneer and Voyager are still, let's say, in the neighborhood of our solar system. And, well, again, we will make some questions about this very complicated universe, small universe, which is the atom. So we think to know what the atom is, and in spite of its name, atom, atomos, not possible, so the Greek origin somehow, it's reflecting the fact that people were thinking that this cannot be cut any further. So contrary to the name, we discovered that welcome, Umberto De Selitz, our director. I have the pleasure to leave the floor to him for some minutes. Then we switch back to the atom. It's a pleasure to have you here.
Good morning. Sorry I'm late, but since in the weekend I live at Padova, that is northern of Italy, I took the train at 6:45 and was just in time, sorry. You welcome them already, I guess, but it is a pleasure to have you here. Okay, it is really a pleasure to have you in our laboratories. As you will see, as you maybe know, we make research in particle physics. We are a public agency, Italian research institution. And in particle physics, we just finished a period of great success with the discovery of the Higgs boson. And one might ask himself, so now what are we going to do? It's finished, but things are just starting, I guess. Moment has not been so excited since a long while. There are many things that one has to understand. You will have a landscape these days, dark matter, dark energy, what's gravity in the general picture, and other things that we even don't know the question to ask. LHC, the machine at CERN, will start again data taking. It will resume next month, in March. And we hope that it will bring us some something that we don't understand, so we have to study. But what we really need is you guys. I mean, I will retire in 10 years, and others will disappear, and we need the young people that are curious, that are excited, they want to work in research. That is a really interesting field. And I hope that you will have just a part of this landscape in these days. So again, it's a real pleasure to have you here. Remember that this is your home. Whenever you want to come and show a laboratory to your friends or whatever, come, just let us know. This is open space, provided you tell us in advance, because there is some safety issues. But for the rest, we are really like to have you here. I will be around in the lab for the rest of the week, so if you need me, just call me. And let me just thank the colleagues that are organizing since years this event, because they do that on top of the research work. So thank you very much, Catalina, and your friends. So enjoy and have a good work. Thank you very much.
Thank you, Umberto. Wait a second, because I just want to show you how many of you want to study physics?
Wow.
You're not. Oh, why? Great. So I'll start with this introduction to the modern physics, so give you a hint of where we have arrived, which are still part of the mysteries. Of course, you will hear much more in the coming days and today from my colleagues about some of these arguments. We try to do a program which embraces part of these mysteries, starting from the dark matter or dark side of the universe. There are two talks related to this. One it's given today and one in the other days. There are some talks related with some applications of the quantum mechanics. So quantum mechanics is a theory which is very, very successful, but for some sense it's very still mysterious because it has not yet reached a consensus among researchers of what's the deep meaning of the things which are described within the quantum mechanics. And there are talks about the gravitational waves, and you have already seen the program, so I don't bother you anymore with this. One thing which I have to tell you is that this is a special year. Probably some of you know that it's the so-called International Year of Light, and this means that this year has been declared by the United Nations Educational, Scientific and Cultural Organization, UNESCO, the International Year of Light, exactly, and there are many, many activities ongoing in all the countries in Europe and in other countries out of Europe as well, and this is a special occasion to celebrate, and that's one of the reasons for which part of our presentations are directed towards this. And you have seen before Fabio Bossi, who gave you a kind of, a welcome on behalf of the research division of Frascati. He will give you as well a talk, a scientific presentation about the so-called dark photon, so the dark light. Okay, so this is just to start that since you are here, I assume you share what Michio Kaku, who is a great physicist, but it's in the same time, he writes very nice book of science for public. I think you share the fact that you want to know, we want to know. So he says that it must be a strange world not being a scientist, going through life not knowing, or maybe not even caring about where the air come from, where the stars at night come from, or how far they are from us. Actually, if you think, you look at the star, now we can indeed reach the measurement of the distance. We can know, we have the means to know how far the stars are. And this by itself, it's such an enormous achievement. So he says, of course, I want to know. And since you're here, I bet you want to know. Maybe you want to know many things, not only in physics. I presume and I hope, actually, that not all of you will become physicists. So it's just, by the way, who wants to study physics? Oh, gosh. Good. Who doesn't? Come on, don't be shy. Okay, that's good, that's good, that's very good. So those who want to study physics, as well as those who do not want to study physics, it's equally important to be curious about so many things in life, and you're at the right age to not only to be curious, but to transform your curiosity, not only in something interesting and important for yourself, like a kind of a job, even if for me it's hard to say my job is being a physicist. There is no job like being a physicist. It's only a passion. You have sometimes the fortune to be paid to put forward, but there are many other things, biology, medicine, genetics. So it's many ways to be curious. So now being curious, let's see what the physicists, what the scientists succeeded to do. So we have I will talk mostly about the modern physics, and the modern physics has some pillars which are very strong, but it's not said that they will stay there forever. Maybe we will find some better theories, which I'll show you some of the points which are, let's say, making us believing that the theory we have today, in spite of the success, should not be the final one. So the pillars are going deep, are deeply rooted in the relativity, which is a very weird theory if you think about just when you wake up in the morning. And this happens to me as well. It's not only to the first time you hear it that you become, wow, it can't be that space-time behave like that. And, but we have reasons not only to believe, we have checked and touched by hand, and I'll tell you, I'll convey to you why this is so. So we will go from the relativity, and the relativity related again with the light, because reminding the year of light, all these achievements were brought to us by understanding the light, so starting to wonder and to question, and Einstein was certainly one, not only one, but one of those who succeeded to arrive farther, very far, and farther than others in thinking about the light. And now, of course, we can even think and imagine and make some fantasies about interstellar travels, so go very, very far, which, well, farther than certainly we can go today, because today we didn't reach too far. Our objects like Pioneer and Voyager are still, let's say, in the neighborhood of our solar system. And, well, again, we will make some questions about this very complicated universe, small universe, which is the atom. So we think to know what the atom is, and in spite of its name, atom, atomos, not possible, so the Greek origin somehow it's reflecting the fact that people were thinking that this cannot be cut any further. So contrary to the name, we discovered that welcome, Umberto De Selitz, our director. I have the pleasure to leave the floor to him for some minutes. Then we switch back to the atom. It's a pleasure to have you here.
Good morning. Sorry I'm late, but since in the weekend I live at Padova, that is northern of Italy, I took the train at 6:45 and was just in time, sorry. You welcomed them already, I guess, but it is a pleasure to have you here. Okay, it is really a pleasure to have you in our laboratories. As you will see, as you maybe know, we make research in particle physics. We are a public agency, Italian research institution. And in particle physics, we just finished a period of great success with the discovery of the Higgs boson. And one might ask himself, so now what are we going to do? It's finished, but things are just starting, I guess. Moment has not have been so excited since a long while. There are many things that one has to understand. You will have a landscape these days, dark matter, dark energy, what's gravity in the general picture, and other things that we even don't know the question to ask. LHC, the machine at CERN, will start again data taking. It will resume next month, in March. And we hope that it will bring us something that we don't understand, so we have to study. But what we really need is you guys. I mean, I will retire in 10 years, and others will disappear, and we need the young people that are curious, that are excited, they want to work in research. That is a really interesting field. And I hope that you will have just a part of this landscape in these days. So again, it's a real pleasure to have you here. Remember that this is your home. Whenever you want to come and show, elaborate to your friends or whatever, come, just let us know. This is open space, provided you tell us in advance, because there is some safety issues. But for the rest, we are really like to have you here. I will be around in the lab for the rest of the week, so if you need me, just call me. And let me just thank the colleagues that are organizing since years this event, because they do that on top of the research work. So thank you very much, Catalina and your friends. So enjoy and have a good work. Thank you very much.
Thank you, Umberto. Wait a second, because I just want to show you how many of you want to study physics? Had, and this is certainly not for claustrophobic people. So if you go there, you are 5 kilometers from both ends when you enter, because the tunnel is long, 11 kilometers. So when you are there, why I'm saying this, because once I was working with an engineer, and he was coming and mounting, and he was sweating and being pale, and at some point, he didn't tell us that he's claustrophobic, and at some point, he was just bumping up, I have to go out, I have to go out. So we had to bring him out and never entered back again. So there are these kind of things which can happen as well, and they are, I'm not saying funny, but well, they are, you have to cope with them. And then you will hear something more this afternoon about the gravitational wave. We have a gravitational wave antenna, which is the so-called Virgo, which is a very peculiar structure where we try to hang on the fluctuation, the small fluctuations which are coming to us out of the explosions of the supernova in farther galaxies than ours. So what we do inside the laboratories, it's, as I told you just a bit more in detail, is on one side we do fundamental research. So fundamental means that we don't have a goal to do some object which does something for the society. This, by the way, happens, otherwise we wouldn't have the cellular phone, the computer, or whatever else. But our main driving force is the curiosity. So what we try to study is go farther on the road to the understanding of the universe in both senses, universe and nature, for the smaller content of it, so understanding the atom, then on the other side, understanding the universe, so the particles and the bigger and bigger structure in the universe and what they produce. We search for gravitational waves, this because we still don't know what the space-time is. So the ultimate structure of the space and time, which goes together with, for those who know, with trying to put together gravity and quantum mechanics. We don't have a quantum version of the gravity. This is very challenging, and it's still some big mystery which we don't agree on, even if there are theories which says that they have thought about and they have a proposal to deal with the problem, but still no convergence has been reached in this. Of course, the convergence usually in physics, it's only reached when you do an experiment which tells you that what you have previewed happens, which doesn't mean that the theory is true, but means it's the best approximation to what we have seen. Then maybe some other theory will replace this one. And this goes very well together with philosophy as well. Philosophy is an extremely useful instrument for the brain and for understanding the world. So we develop theoretical models, I told you, but of course we do this in the same time as we do the experimental research, because we have to check our ideas. And we are lucky enough to have here this accelerator, but the accelerator works with particle detectors. So we have many laboratories which are developing eyes for scientists, and our eyes are the particle detectors. Beyond this, so particle detectors and accelerators, we are doing research which is very important for society. Part of it is, for example, the biomedical research. So we are using our beams of radiation from the Daphne accelerator, and one of the working groups is related to this with synchrotron research, to irradiate different materials, either for industry or unknown structure, or even to understand the biological activity of some tissues. And in order to analyze the data, we need to have a strong net of computing and of programming, so information. So based on this, we are contributing together with colleagues from all the world, and there are many institutes as ours in the world. We contribute to expand and to deepen our knowledge in both dimensions. So on one side, with the accelerator, we go towards smaller and smaller structures, understanding what stays inside the atom, and not only in the atom. I want to tell you that the main part of the particles which comes from an accelerator are not related to normal matter, are particles which are living like that. Bam! When I do like this, the lifetime, my kick like that is many, many times longer than the lifetime of that particles. So these are kind of particles which are born either at accelerators or from the cosmic rays interacting with the molecules of the air, so we want to study them as well. And on the other side, with the satellites and with the all kind of observatories, we go towards bigger structures. So on this kind of, actually, this is not even linear. It should have been circular, because what we see is that our understanding of the micro-universe goes back to explaining maybe the mysteries of the bigger universe, namely the dark matter and the dark energy. So all what seems to fuel the universe dynamics, all this expansion, all these vortexes of galaxies one around the other and of the stars inside the same galaxy seem to be fueled by the dark matter and by the dark energy. And we have the means today to study them in the laboratory by pushing hard on the limits, both on energy and of intensities of the beams. That's why the director was saying that in March, so less than 1 month, it will start the Large Hadron Collider again, and that's definitely one of our biggest challenge of humankind, not only of us, the physicists, but it's an achievement like the best artworks of all the humankind. So I'll try now to give you some details related to both these type of studies which we pursue in the dimensions of world knowledge, and I'll start with the micro-universe, go very fast, because I assume that if you are here, even if you didn't study at school everything, since you are passionate, you know already how an atom is. So what has happened in a bit more than 100 years was that what was considered atomos without structure has become completely complicated. So has become a very, still a very mysterious structure, because we know now that the atom, here we have a wrong model. This I put it here, the Thomson's atom, where it was, a first tentative to explain where are the electrons coming from, because people was happy with considering the atom without structure. Only that at some time the electrons started to pop up from the experiments with the tubes under vacuum. Since it was obvious that electrons are charged particles with a mass much smaller than the atom itself, they should have been hosted in the atom. How? So this was the first tentative of Thomson, who tried to put them in like in a pudding, and it was a failure. But physics, this is maybe sometimes people do not tell you, it's composed of 90% of failures. The success is very small, but the failures are teaching you the road towards the true answer, so are equally important as the success. So this goes in life as well. Don't be afraid to fail. It's much worse not even to try. So just try. If you fail, it's no problem. You start again. So failures are teaching us something. And this was the case of this model. But then we quickly after a few years, Rutherford, by doing experiments, kicking a foil of gold, succeeded to understand that the atom has a small, dense, and very, very, where all the mass of the atom, it's the nucleus inside around which the electrons are vortexing. This is the same image as this, only that in this way you combine the knowledge from the quantum mechanics, so you have the orbitals. I remember when I was by your age in school, I was very much confused that in physics I was learning this. In chemistry I was learning this. And hardly I could put them together. What does it mean that the s orbital is kind of a big sphere, while the p orbital is kind of two lobes, and so on and so forth? How this goes together with this, that they go nicely together on the orbits like the... Well, actually, an image closer to the reality, if we think about the energy, it's the one which we mostly study in chemistry, because it combines the quantum mechanics, which tells you that there is no way to know the position of a particle with high precision and in the same time its momentum. So it's a complicated story, but sometimes rather confusing, but that's like that. That's one of the things which the quantum mechanics, it's still making us fighting furiously. And there are seniors, professors who are 60, 70, who are almost kicking each other for the meaning of this type of things. Then we have learned that inside the nucleus, there are smaller particles, which are the protons and the neutrons, which we now know very well, even if it's not yet very clear how big the nucleus could be, as I told you before. And there are inside, that's the last thing which we have learned, that inside the protons and the nucleons, there are even smaller constituents, namely the quarks. And the quarks are 3 for each proton and for each neutron. Of course, they are not exactly the same. I mean, they are always 2 types of quark, up and down, but there are 2 of a kind and 1 of a kind, interchanging, going from proton to neutron. And of course, now the question would be, is there something else smaller? Is that the quark, it's composed of something smaller? The true answer is that what we can say today, that if it is composed of something smaller, that something should be smaller than 10 to minus 18, 19, 10 to minus 19 meters. Why this? Because our accelerator do not have energy bigger than kicking off structures smaller than that. So if inside a quark there would be something like 10 to minus 25 meter, we don't know. We don't have energy. It's like when you play the billiard, no? If you have a ball of balls on the middle of the table, if you kick them strongly, they pop out and you can see them. If you kick the ball like with a very small energy, it will go there and nothing will happen. That's the same here. We don't have the energy today to say whether the quark is composed of something or not. Of course, as in the best tradition, the theoreticians who are looking farther than experimentalists can check. They are divided. There are the majority who says that the quark, it's the ultimate structure, but it's not a point full of energy or whatsoever. It's the manifestation of the so-called string. This goes in the string theory. So it's a kind of a string which vibrates in the 11-dimensional space. I'll come back to that. Of course, we don't have the possibility to check this. Why? Because this string should be 10 to minus 30-something meters. So that's the reason for which we experimentalists look at the theoretician and say, okay, goodbye, come tomorrow when you tell me something which is within the reach of the possibility to check without building an accelerator which goes from here to the Andromeda. I can't do that. There are other theoreticians, which is, well, maybe smaller number, who are saying that the quark is composed of something else. Now you have to know that fortunately in physics, differently than in politics, the majority is not always right. So here, who is right, it's right, you prove it. You have the mean to prove it, and once you prove it on the ground, even if you are only 1 against 100, the 100 should be convinced that you're right. So we have to wait and see, and not wait and see, and do something on both things. So the particles which are composing actually the atom goes in this standard model, which is our best instrument to know the nature. So the standard model puts together all the particles, the minor, the smaller, the so-called elementary particles we know. So there are the quarks here. Up and down are those which are staying inside the proton and the neutron, but there are more quarks, and these are produced in the accelerators or in the cosmic rays, so they are in the body of particles which are produced in this way. We, in the Daphne accelerator, produce particles which are having this quark called strange, while at CERN they produce particles which are having all sorts of quarks. Here you see another family of particles which are called leptons, out of which the most representative is the electron, but there are some other, then the neutrino, which is among the particles in the standard model, the most mysterious one. Why? It's enough one feature to be reminded, to give the flavor of that. We know that they have a mass, but we don't know how big this is. actually how small it is. We know that they have a mass because they behave, they oscillate, they have some features which only particles having a mass have. And we didn't succeed to measure this mass. It's certainly much, much smaller than the electron one. But since the particle is neutral, it interacts very weakly with you, we have huge problems to estimate this mass. So this is a task which has to be dealt with. If not for else, because the universe is full with neutrinos, so they certainly are part of the dark matter, but we don't know how big, because we cannot say how big they are. The last particle discovered is the Higgs boson, and this fulfills the standard model. So one might be happy, I can greet you and say goodbye, this is the end of the physics. Fortunately, it's not like this. It's not like this for many, many reasons, but let's say the biggest reason, and it would be enough, there are many others, is the fact that there is nothing in the standard model speaking about gravity. So standard model speaks about electromagnetic interaction, about the nuclear forces, and that's more or less all. If you would ask the quarks, how is the gravity among them, and they should have a gravitational force among them because they have a mass, there is nothing, absolutely no way to compute it in the standard model. There is no graviton here. So particles in the standard model exchange force carriers. These are the photon for the electromagnetism, the gluon, and the W and Z boson for the other forces. But there is no graviton, there is nothing. Now one might say, how could that be? Well, the standard model combines together the quantum mechanics, the relativity, and the knowledge, what we measure in the lab. The fact is that Einstein himself tried to compute the gravity in quantum style. And of course, the standard model was not there when Einstein tried to do that, but he tried to make a unified version of gravity and electromagnetism. And he failed because you compute, you try to put the challenge and you calculate many, many pages and you arrive at an answer, which is infinity. So the force of between two quarks, gravity, in the standard model-like version, it's infinity. And you do not go beyond the infinity. And this is a very bad problem. Of course, it's a very bad problem. One might wonder, why is like that? Because if you remember, the gravitational force behaves somehow very much like the electrostatic force. No? The electrostatic force goes like 1 over r square, 1 of the square of the distance. But there is a minor difference which makes all the deal in the end. In the electrostatic force, you have the attraction, no, between the two different charges, and you have the repulsion between two charges which are similar, which are alike. In gravity, you only have attraction, always. There is no repulsion. That's the origin of all the problem with the gravity in the quantum version of standard model. So this difference that there is always attraction makes so that the gravity is not quantizable as the other interactions in standard model. And so the standard model does not speak about gravity. Is this a problem? It's an enormous problem. If not for else that the universe, it's gravity. All the structures in the universe, the galaxies, the solar system, are not handled by nuclear forces. Of course, if you look inside the star, yes. But if you look at the dynamics of the galaxies, the gravity is what matters. So we have to see what we can do with this. And I'll come back later on. So these are the things which we are trying to pursue. So understanding further the standard model and what goes with the name beyond standard model. Now we are working at the theories and experiments which are beyond standard model. This is what it's kind of ID card of our laboratory. So we are around 1,000 in the end because we have a staff of about 350 plus external user, which means PhD students or researchers which come to work with us, which means that what the director told you, that just join us later on if you wish to, either as colleagues or just for visits. There is place to come and be with us in the challenges which we are undertaking. So this is what kind of ID card of what we are doing. And this, it's a picture of our laboratory from above. And here we have the main accelerator, the Daphne machine, where we do experiments I'll tell you about in a while. And as well, we have a beam, which is the Daphne light, which is the synchrotron light. Then we are having a structure here which is trying to pursue new accelerator techniques. So we don't only use accelerator, but we try to invent new items, new ways to accelerate the particles. Because I told you that reaching higher and higher energy, which might be necessary if you want to kick off the compositeness of quarks, for example, or of something else, you need to do more compact accelerators. So already the Large Hadron Collider, it's 27 kilometers, it's far, far too big. If you would wish to go 10 times more in energy, you can't imagine that you build an accelerator from Sicily up to Norway, up to Oslo. It's not the way to do. So what you have to do then is to try to increase your power of accelerating particles. So in 1 meter to accelerate 10 times more. And the tradition here in Frascati goes like accelerator having been built ever since we were starting as an institute. We started with not with a collider, with an electrosynchrotron, which is an accelerator which delivered a beam of particles, but then we went on beyond one beam of particle. So it was realized that having only one beam of particle kicking a target, whatever the target is, a gas, a liquid, or a piece of metal, or whatever is, has limitations. Because when you kick a target with a beam, and we know how to do one beam, the problem is that what you have inside, it's rather complicated, and you never succeed to study the only process you would like. For example, you want proton-proton, you can't, actually go only for proton-proton. You go proton, electron, proton, neutron. It's a lot of complicated things. Then, this first one, I don't know if it makes you a bit, what is that? Matter, it's empty. Well, this goes back to how the atom is done. So the atom has a small nucleus in the center, and the electrons going far, far from the nucleus. It's like if we imagine, and I presume that you have heard this already, that if the nucleus would be a ball in a soccer field, the electron would be far out of the field. So the rest, it's empty. Empty doesn't mean the perfect vacuum. The perfect vacuum does not exist. Vacuum, it's a soup of fluctuating fields dictated by the quantum mechanics. So with these problems, it appeared immediately as a clever idea to, instead of having only one beam of particles, to collide two beams of particles, actually of one particle and another beam of antiparticles, because then by annihilation, you can use the mass of the two particles in the budget of the energy to create other particles. And this idea was pursued here in Frascati in the 50s under the leadership of Bruno Touschek, who came from Austria. He has a very difficult life. He lived his last years in Frascati, had a difficult life because was made prisoner in the Second World War because he was of Jewish origin, so he had was nearly to die by starvation, and had a difficult life, but was strong to survive and to come here and not to be a destroyed person, but to be a leader. So he led to the construction of the first ever in the world particle-antiparticle collider. While it might look like being easy, it's not easy. Why it's not easy? Let's imagine the following thing. I stay here, some of you goes in the back of that room, and we have a bag with very, very small balls, like 1 millimeter in diameter. Now, if I take 3 of them, you take 3 of them, say, let's try to meet in the center. It will be very hard. No, because they are very small. In order to increase the possibility that they hit each other, you have to throw many, maybe 1,000, 10,000s, that some of them will hit each other. Okay, then what means? That you have to put many particles in a single beam. How many? Billions, hundreds of millions and billions. It's very difficult because these particles are of the same charge, so they are electrons. All are having negative charge or positrons, and they don't want to stay together. because they are having repulsion. So they kick each other, they are very, well, not happy to stay together. So if you don't oblige them to stay together, they will leave. They will live away, and you will have nothing to meet in the center. So the accelerator physics, it's very complicated, and you need to find the field configuration, the magnet, the electromagnetic fields. To each time one of them wants to go, bang, you bang him in the head and put him straight back in the beam. It's not always easy. In the end, you still lose some of them, but you do your best to keep as many as possible and make them meet and generate the processes you want to study, something like that. So they meet, they annihilate, in the case of particle-antiparticle, and depending on the energy you put in, you can generate particles of different type. So by conserving the energy, the total Einstein-like energy, in the final state, you can reproduce, by transforming part of the kinetic energy in mass, you can have different particles. And that's the key notion of whatever happens in any accelerator in the world. You transform energy from known particle that you can handle in mass of particle you never have seen. This is how Higgs was discovered in the end. You transform the energy of the beams of protons in somehow the mass of the Higgs boson or in whatever else, and you study it. So this is how the life goes in an accelerator. So of course, when Bruno Touschek, now you understand why this room is dedicated to him, so he went to the government and said, I want to build this machine. And they told him, whom else in the world has it? And he said, nobody. We don't give you money. We give you money to build a prototype. If you succeed to convince us this works, we will give you money to build accelerator. And this happened in very few years. In a couple of years, they succeed to build the first piece of history. So the ADA, Anello di accumulazione, which you can see. There is the original in our entrance, so if you make a round, you can still see it in our museum. So they succeeded to do this and to prove the concept works. So they went back to the government, they got the money, and they built the first machine in the world by using the electron-positron collider to study the standard model by that time. This worked for more than 20 years, then was replaced by a more modern machine, the Daphne collider, which looks very complicated, and in fact is very complicated, since it has more than 200 magnets of a circumference of around 100 meters, where we study type of particles. The same concept worked at various accelerators. All the colliders in the world are basically using the same head-on collision between beams of particles and antiparticles, or only particles, as in Large Hadron Collider. God. This was to awake those who were sleeping. So this is basically how Daphne works. Of course, we have to prepare to generate beams of electrons and positrons. The positrons, which are antiparticles, antimatter, we don't have freely going in the universe, so we have to produce them. We produce them by kicking beams of electrons, which are easy to generate. Even in the old type of TV, with the cathode, you have a beam of electrons, so you have an accelerator. This is more or less what we do in a linear accelerator. We kick the electrons here. The electrons hit on a piece of metal, and out of the interaction, many particles are created, among which positrons. Then with magnets, we are sucking only the positrons, throwing away the others. So we have positrons as well. So we preparate them, we are compactifying them in a machine, and then we inject them in Daphne, which is an electron-positron collider with two rings, one for the electrons, one for the positrons. And then we have experiments here who are studying the physics which happens there, which is the physics which happens there. Again, we have annihilation of electrons and positrons. In our case, the energy of the beams is tuned such as to generate the phi, the so-called phi particle in the final state. We have kind of hundreds, thousands, or something like that of phi particles, but the phi has a very short lifetime, something like 10 to minus 20 seconds. So it doesn't go too far. it decays immediately in other particles, which are called kaons. Actually, these are what we are caring about, because the kaons are having in their body the strange quark. And the strange quark, it's in the standard model from a family which is not the one out of which we are done of. So it's not the quarks out of protons and neutrons. It's a family which is, well, it's a strange family. So we want to understand better the strange family and the strange quarks, so we study these kaons. The kaons themselves live shortly, something like 10 to minus 8, some of them 10 to minus 10, some other, but with respect to the phi, it's infinitely longer. In 10 to minus 8, 10 to minus time, we do have time to study something, because if you make computation, you see with 10 to minus 8, the kaons travel some meters, so you have some time to study them. How we do? Well, we do different type of experiments. One is the so-called Siddharta experiment, where you use the kaons to put them in atoms, like in a hydrogen atom. They are negatively charged, so they kick off the electron, they replace it. But since they are much, much fatter, they are 1,000 times fatter than the electron, their ground state, it's not the one of electron, but they go much closer to the proton. So they form a very small atom. And what you want to study is the way in which this atom behaves. So how is the rule of this atom, and how the kaon, which has the strange quark, interacts with the proton. And this, a part of being interesting by itself, it's something which tells you of what might happen in the stars, in the neutron stars. Because in the neutron stars, the strangeness might play a role. So you might have this kind of kaons in a neutron star, which would become strange stars, and it has many implications, which, if you want, I can tell you some other time. This is instead the experiment which is now on the machine. It's the biggest experiment. It's called Chloe, which does itself very fascinating studies. It's a complicated experiment which contains many different detectors which are tracking the particles, so like this. So it studies, this experiment, it studies the difference, for example, between the way in which the kaons behave with respect to the way in which the anti-kaons behave. And maybe you know it goes under the CP violation that, strange enough, the laws in the world of particles are different than the laws in the world of antiparticles. So the matter and antimatter behaves differently. By a very small, the difference is very small, but what we try to do in different experiments is to understand whether this difference is still enough to justify what happened with the antimatter. Because in our belief, in the origin of the universe during the Big Bang, the quantity of matter and the quantity of antimatter was generated in the same amount, so equally. If this is so, either all should have been annihilated and the universe should be a universe of photons, or it should be somehow, a very big dynamics of annihilations. So what we believe is that antimatter died. What means died? Means that the laws of physics, and this is what we measure, that there is a difference between matter and antimatter disappeared. Now you might say, well, oh great, you have solved the antimatter problem. No, because what we have measured up to now, the difference, it's not big enough to justify the disappearance, the complete disappearance of antimatter. So what we are trying to do is either to measure more particles which are behaving differently, or to understand whatever else might have happened. So we are on the good road, but the road is still very long, and we have to go a long way. Then we do applications. So with the beams which are there, we study medical science. So the group which is going to the synchrotron will have the possibility to learn more about this. And as well as I told you, we try to use different accelerator techniques. So not only to learn and to build accelerators like Daphne, but as I told you, we are not happy with the fact that in order to study what's in the quark, for example, we might build an accelerator all around the equator and it's still not enough. So we want to do more energy in 1 meter. Like ideally would be to have Large Hadron Collider in this room. So this is the so-called Tabletop Accelerator. And to do this, it's not enough to do more better magnets or whatsoever. You have to change your head. And you change your head by trying to use completely new concepts. One is to use the lasers beam, so to use the plasma, so to use different techniques which are making so that what you have in the end is to create a wave. In this case, in our case, it's an electromagnetic wave, which is pushing the particle like a surfer. So we want to have a perfect wave like the surfers which are going in the ocean, and they look always for the perfect wave. So the perfect wave in our case would be the one which is pushing the particle in phase and brings it to us with an energies never reached before. And this is something we try to do, and we are presently doing, and we have here a machine which is trying to do that. As an output of that, we have applications, and one of the applications is that we use the beams which we are creating, for example, in medical diagnosis. With the beams we are creating, we have much more clear details, you see here, which helps the doctors to tune their diagnosis in looking, for example, for structures in a kind of a breast cancer. Here is mammography with a monochromatic radiation with respect to the standard one, so you see more details. So this is a parallel application which goes together with fundamental research. We are as well studying the gravitational force, but since you will have this afternoon talk about the gravitational waves, I'm not going to insist on this. I'm only going to tell you that, now what? Where is it? Now. So what we try to do and what we can do here in the laboratory, we have a so-called gravitational antenna inside here, which is looking for signals which might come from explosions of the supernova inside our galaxy. So it's a gravitational cryogenic antenna. I think you will have the possibility to see it, which is vibrating whenever a gravitational wave could reach us coming from a supernova in our galaxy. Well, the oscillation is very small, and Viviana will tell you probably all about this, so I'm not going to spoil her talk by telling you details. Some of my colleagues are working in experiments at Large Hadron Collider by undertaking many responsibilities in the 4 biggest experiments there. Large Hadron Collider, it's an underground accelerator, 100 meters under the ground, and this is not only due to the fact that if you put it on the ground for 27 kilometers, somebody might walk in the forest and jump into the accelerator and break it, but it's mainly due to protect us, because it's a very highly radioactive environment. So the beams are activating the materials which are becoming radioactive, so it's not very good. These are sketches of the 4 biggest experiments which are installed there. And this is what actually people have seen when we tell you we have seen the Higgs boson. This is not true. We didn't see the Higgs boson. We have seen his daughters and sons. We never have seen the Higgs boson. We have seen the particles which are generated when it dies. So the photons which reconstructing their mass are here. So usually physicists are doing histograms like this. And when we see a bump where we don't expect one, we have a so-called signal. This is our main instrument. And the signal might be due to many things. Might be a mistake. This happens very often. Might be a signal due to a different particle. Might be everything. So you have to do many checks in order to be sure that the invariant mass of photon corresponds to what we believe to be his mother. In this case, it's the mother of the 2 sons is the Higgs boson. So when we say we saw the Higgs boson, it's not true. We never saw the Higgs boson. We have seen the particles coming from his decay. This is what we have seen. But we are convinced that this is the proper, that there is no other signal which could have generated this. So they belong to the Higgs boson decay. And these are the persons who have created the theory, who got the Nobel Prize immediately, François Englert and Peter Higgs, properly and rightly. And, but still the road is very long. and I bring you back to the gravity, to the fact that we don't have a quantum version of the gravity. Einstein was looking for it for the last 20 years of his life. We are still looking for it. We are maybe a step forward, but we have other mysteries, which you will hear some lectures about. We have mysteries related with what the universe is made of. Because when you look at its dynamics, so what happens of the rotation of the stars in the galaxy, or what happens with the universe expansion, which is accelerating, you can explain them only if you introduce dark quantities in the universe. So you have to put both dark matter, which is explaining the rotation, for example, pattern of the stars in the periphery of the galaxy, but you have as well the dark energy, which cannot be of gravitational origin because pushing the universe to accelerate, it's behaving like anti-gravity. And since we know nothing in the universe which behaves anti-gravity, we call it dark energy. And we have some hints of what might be, but our hints are so far from a check or even from an answer which convinces us all. So if I dare saying the dark energy is our biggest mystery because it governs the dynamics of the universe and the fate of it. And even if we might not be here to check whether our theory is correct in some like 100 billion years, it's still interesting, challenging, and compelling to think about how the universe will evolve and what will happen in the end. And people who are doing this, you recognize him. Among them, there is definitely this weird and tremendously successful, ambitious and wonderful Stephen Hawking. I don't know if you have seen the movie, The Theory of Everything, which undergoes now. It's more on, well, physics and his first marriage. But he's definitely one of those characters who contributed to the modern physics. He's still every now and then popping up with some statements. Yesterday I read a statement. It was very funny because NASA was saying, you know that NASA every now and then it's making announcements which are bombastic. So NASA was claiming that it's the right moment we send messages to the extraterrestrials, as if somebody stopped us to do this before. So it's not that we have many means to do that. But as soon as they said, we will send messages to the extraterrestrials, he came and said, no, that's wrong. It's dangerous. Stop doing this because they will come and eat us or whatsoever. So, well, things in physics are not always looking for the Higgs boson. It's something more challenging which involves the society, involves things and thoughts and feelings and not only physics. So he is one of those who was working mostly on the gravity. It's not the only one. There are many others undertaking this challenge of the gravity. And the theories about quantum gravity not only bring us to the understanding of what happens in the universe, but might help us to have the interstellar travels. And one of the proposals, which even if weird, I read the word, do you know the word quirk? Quirk physics. So it's something which crazy invention. So this kind of drive which is using negative energy to create a wave in the gravity structure of space-time structure to push you far and far with a speed which is equivalently much faster than the light. So this is something which again comes as a side effect of our studies. And now I'm approaching the end with this, physics, it's still full of mysteries. It's still full of things to be done. I only showed you part of them. You will have the opportunity this week to learn much, much more, and it's still not enough. There is plenty of things to do. But I want to close with these quotes from Einstein. So there are two ways to live. You can live as if nothing is a miracle, or you can live as if everything is a miracle. And addressing to the young ones, try not to become a man of success, but rather try to become a man of value. And I think that nowadays, in this Europe which is cracking, in this world which is even more cracking, we need you. We need you and your force and your energy and your good willing to do good things, to become men and women of values and to bring not only our knowledge farther, this probably will happen, but to bring our humankind farther. And I think that my generation and the previous ones, we rely on you. So try to become men and women of values. So thank you very much, and I hope you will enjoy this masterclass, this school, and I hope you will make friends, and the friendship will last during the years. So let me see if I'm, okay, so this is our laboratories. We are happy to have you here. If you wish, just walk around during lunchtime or whatsoever, and we are at your disposal, not only now and this week for questions and for even advices, but you who is interested can contact us even after for advices by email and to meet further and to keep our relationship. So don't forget who is wishful to do the interview, go to give the name and enjoy this week. Now we will have a coffee break. Thank you very much. And